Good day, dear student. Today we will have a lecture on discipline Propedeutics of Dental Diseases, Therapeutic Dentistry. The theme of our lecture is Materials for Filling Carious Cavities. Relevance of the lecture: knowledge of the characteristics and techniques of preparation dental filling materials allows you to make the best choice of filling material depending on the clinical situation, and is also one of the conditions for successful dental treatment. The purpose of the lecture: to study the classification and characteristics of dental filling materials. Filling: intermediate or final stage treatment of hard tissue of the tooth, associated with filling the defect with filling material. At the final stage, this allows you to restore the integrity and functional activity of the tooth. Oral factors: temperature fluctuations, increased constant humidity, electrolyte environment, properties of filling materials: physical, chemical, mechanical, aesthetic, technological, and biological. Physical chemical properties of filling materials. Physical: it is density, thermal, optical. Optical is color, transparency, shine, fluorescence. Physiological and chemical: solubility, chemical, electrochemical corrosions for metals, oxidation, properties of curing reactions, and it is the adhesive properties. Straight, stability, elasticity, plastic, for compression, straight, bend, shift, and torsion. Types of deformation. And in this picture we see types of deformation. First, it is a compression, straight, bend, shift, and torsion. In this slide we see change in the direction of the force of masticatory pressure acting on the filling and the walls of carious cavity, depending on the axis of inclination of tooth. In these slides we see change in the direction of force of masticatory pressure acting on filling at the walls of the carious cavity, depending on the formation of carious cavity. 1 and 2 picture it is correct, and third picture is incorrect. Chemical properties of filling materials. Interaction with tooth tissues, with the environment of the mouth, oral liquid, materials among themselves, mechanisms of adhesive interaction of material with the surrounding tissues, curing materials. Requirements for permanent filling materials by Miller, late 19th century. First, chemically resistant, minimally soluble, under the action of saliva of food. Mechanical strong. Conform to the appearance of natural teeth. Abrasion resistant. Tightly adhere to the walls of the carious cavity. Maintain shape and volume for a long time. And 7. Good handling properties. Plasticity for working time. Eight. Minimally dependent on moisture for filling and curing. Biocompatible. Be harmless to the pulp, hard tissues of the tooth, the mucosa of the mouth, and the body. Do not contain toxic components. Anti-carious action. Low thermal conductivity. The coefficient of thermal expansion is similar to the coefficient of tooth tissues. X-ray contrast. Long shelf life do not require special storage and transpiration conditions. Main characteristics. Adhesion. Sticking. The connection between dissimilar surfaces. Filling tooth tissues. Mixing time. Recommended, or the maximum allowable time during which the material components are mixed. And working time. From the beginning of mixing the material, insertion into the carious cavity, filling formation. Cure time, during which the initial curing of the material occurs. Maturation time, during which chemical reactions are completed in the material and its final chemical structure is formed. Abrasion, the loss of the mass of seal is expressed in the loss of mass of sample to its area in contact with the adhesive. Thermal expansion coefficient. During curing, polymerization of the filling and in response to thermal stimuli should match the tooth. Marginal fit. Adaptation to the walls. The proximity of the filling material to the walls of the carious cavity depends on shrinkage, thermal expansion coefficient, and adhesion. Stability of the volume and shape of the filling. Spatial stability. The ability of a material to retain its shape and volume, not to shrink. Shrink. Reduction in volume during the curing of the seal due to chemical and physicochemical processes that occur during the structuring of the seal. With a large shrinkage, a gap is created between the walls of the tooth cavity and the material, which leads to a recurrence of caries. Straight. Resistance to fracture to compressions determines the ability of the seal to withstand the load. And in this slide we see composition schemes of cements. Zinc oxide and phosphoric acid, it is zinc phosphate cements. Zinc oxide powder and polyacrylic acid liquid, polycarboxylate cements. Polyacrylic acid and alumosilicate glass powder, it is glass ionomer cements. And alumosilicate glass and phosphoric acid liquid, it is a silicate cements. Polymeric cements include glass ionomer, polyalkanate, alkanate, and glass polyalkanate, created by combining the properties of silicate and polyacrylic systems. The first glass ionomer cements developed by Wilson and Ken in 1971 and released in the early 17th century in USA by Detroit. Traditional classical glass ionomer cements consist of powder and liquid. Curing phases of glass ionomer cement: dissolution of hydration, release of ions, leaching of ions, thickening or primary gelation, initial unstable curing 7 minutes, hardening or dehydration, repainting, final curing 24 hours, acid-base type of reaction. Adhesion of glass ionomer cement with dental tissues, carried out by two mechanisms. The first mechanism, the formation of chelate compounds between macromolecules of polycarboxylic acid and calcium hydroxyapatite of enamel and dentin. And the second mechanism, it is formation of hydrogen bonds between polycarboxylic acid macromolecules and dentin collagen. Classification of glass ionomer cement. By application, according to McLean, 1988. Type 1. Glass ionomer cement for luting. Type 2. Restorative glass ionomer cements for permanent filling. A. Aesthetic. B. Reinforced. C. Condensable. Type 3. Fast hardening glass ionomer cements. It's one for gasket, liner, and fissure sealants. Type 4 for filling root canals. Second, according to the release form, it can be powder and liquid, paste, and only paste. And in these slides we see glass ionomer products, powder and liquid, powder and liquid. Premature capsule. Note the cements being expressed from the capsule tips. And paste dispenser. Three, according to the content of polyacrylic acid. Can be water, semi-aquatic, anhydrous, aqua cement. Aqua cement powder contains lyophilized polyacrylic acid. The glass acid ratio is optimal. 4. By chemical composition and curing mechanisms. Classic 2-component glass ionomer chemically cured cements, powder and liquid system. 2-component chemical curing aqua cement, true. Hybrid dual cure, hybrid triple cure, and 1-component light curing polymers containing glass ionomer cement filling. Hybrid glass ionomer cements. The composition includes a light curing polymer resin. During the curing of glass ionomer cements, strong bonds are formed between the polymer and glass ionomer matrices. Less sensitive to moisture and dehydration. Height straight. Harden without the formation of microcracks. Increased adhesion force with tooth tissues. Harden only under the action of light from a photopolymer lamp. Hybrid glass ionomer cements double curing. Cure mechanisms. The first, when powder and liquid are mixed, the typical chemical curing reaction of glass ionomer cement occurs within 24 hours. When light is added from photopolymer lamp, composite reaction of curing the polymer matrix. As a result, a dense polymer framework is created, which ensures the strength and stability of glass ionomer cement. The glass ionomer and polymer matrices are combined. And in this picture we see a photopolymer lamp. Hybrid glass ionomer cement triple curing. Cure mechanisms. First, light curing polymer matrix. Second, chemical curing of the polymer matrix. And third, glass ionomer curing reaction. Single component light curing glass ionomer cement. Have a polymer matrix that hardens under the action of light and a glass ionomer filler. During curing, only the photopolymerization reaction of the polymers occurs. The glass ionomer reaction does not occur. that is, chemical bonds with the tissues of the tooth are not formed. Positive properties of glass ionomer cement. First, chemical adhesion to tooth tissues. Second, good chemical adhesion to various filling materials. Third, high biocompatibility with tooth tissues. Non-toxicity. 4. Anti-carious action. 5. Compressive straight. 6. The coefficient of thermal expansion is close to that of enamel and dentin. 7. Low thermal conductivity. 8. Acid resistance. 9. Low modulus of elasticity. 10. Low polymerization shrinkage. 11. Satisfactory aesthetics. 12. Color stability. 13. Insignificant release of hurt during hardening. 14. X-ray contrast. 15. Compatibility with other dental materials. 16. Easy to use. 17. Cheap. Negative properties of glass ionomer cement. Sensitivity to moisture during hardening. Slow chemical hardening. The color of the filling is established after 24 hours. Insufficient aesthetics. Fragility. Preparation of glass ionomer cement, powder and liquid. For example, Cavitan Plus. Ratio: 1 scoop of powder and 1 drop of liquid. Optimum cooking temperature, mixing temperature, 20-25 degree. Shake the powder before use. Do not compact the powder in the measuring cup. Remove excess powder in the measuring cup, if with a slide. Measure the liquid by moderate compression of the walls while in a vertical position. Mixing: on a disposable paper pot or glass plate, plastic or stainless steel spatula. Knead for 30 to 45 seconds. Properly prepared cement is plastic. Protection with coating varnish. In the first hour after curing, glass ionomer cement is sensitive to moisture ingress. Therefore, after curing, the seal is covered with a protective varnish. The varnish is applied with an applicator and dried with a stream of air for 10 to 15 seconds. Do not use a very strong air stream to avoid varnish shifting. Conditioning. Conditioning the walls of the carious cavity to improve the adhesion of the glass ionomer cement. Conditioner 10 to 25% aqueous solution of polyacrylic acid. Applied to the tooth tissues for 10, 15 or 30 seconds. Then rinse with plenty of water. The acid removes the smeared layer from the dentin surface. The plaques in the dentin tubules remain. Dentin demineralization practically does not occur. A smooth surface of dentin is formed. High humidity of dentin. Calcium and phosphate ions are activated. Relics lightening 2. Preparation of glass ionomer cement paste. Relics lightening 2. Self-curing. Fluoride releasing glass ionomer cement. Consists of base paste and catalyst paste. Paste is squeezed out automatically in the same volume. The ratio of the actual dosage weight is 1.3 to 1. Etching enamel and dentin. The organic matrix is hydrophobic. Marginal adhesion of the composite material to enamel and dentin has deteriorated. In 1955, Boncourt suggested etching the enamel for 2 minutes to enhance adhesions. For 85% phosphoric acid solution. Optimally etching enamel with 30 or 40% phosphoric acid solution for 13 seconds. Enamel demineralization occurs. Enamel plus acid, it is partial dissolution of mineral substance of enamel prisms occurs. From the surface of the enamel, a layer 10 micrometers thick is removed. Micropores of 5 to 15 micrometers are formed. The enamel is embossed honeycomb-like structure. And in these slides we see enamel surface after etching according to scanning electron microscope. This photo due Ericsson. Etching dentin 1978 Fujiyama. Pickling 32 or 37% phosphoric acid. Solution: export to dentin for 15 seconds. Wash off with plenty of water. Acid removes from the surface of dentin smear layer, plaques in the dentitional tubules, and demineralization of dentin occurs. Exposure of collagen fibers. In this X-rays, in this microscope scanning, we see etching dentin. First slides, we see smear layer and dentin plaques, and second microscopes films, we see dentitional tubules open and exposure of collagen fibers. In this electron microscope, we see dentin surface after etching according to scanning electron microscope. It's made Ericsson. Etching solution or gel. Concentrated inorganic acid to completely remove the smeared layer and create a microrelief on the surface of enamel and dentin cement, which contributes to the penetration of components, the adhesive system, into the hard tissues of the tooth and the formation of a full-fledged hybrid layer. Conditioner. This is a solution containing organic or weak inorganic acid. It's used to remove the smear layer from the surface of the dentin. Acid release forms for etching. It can be solution or gel. If the solution, it is impossible to apply to the tooth tissues. Uncontrollable, the liquid spreads. If the acid is colorless, it is impossible to control acid flush quality. It is impossible to introduce acid into the carious cavity if there is moisture in it. Decreased acid concentration, the depth of micropores in enamel decreases. Acid exposure 15 to 13 seconds. Etching 60 seconds. Destruction of enamel prisms. Etching for 120 seconds. Insoluble calcium compounds are formed, which reduced adhesion. And in these slides we see acid for dental etching in gel and how this used in tooth. Etchings. It can be for enamel, for dentin, and total for enamel and dentin. Etching of dental tissues. How long do we spend? 30 seconds. So much time we wash. 30 seconds we wash with water. Adhesive systems. Adhesive connection bonding. The connection of two surfaces with an adhesive. Adhesive is a sticky adhesive substance that interacts with two surfaces. Enamel adhesive bond is a hydrophobic monomer and solvent that provides micromechanical adhesion of polymers strands of composite materials with enamel. Dentin adhesive. Primer. Hydrophilic monomer and solvent. Micro and nano adhesion of composite material with dentin. Enamel and dentin adhesive. It's named bonding system, bond system, and adhesive system. It is solution, contains bond and primer. And in this picture we see Admira bond for enamel, Solo bond plus for dentin, and primer and bond for enamel and dentin. Primer and bond. Solvent. It is a chemical substance. Include acetone, alcohol, water, or a combination of them. Promotes the penetration of the components of adhesive system into the tissues of the tooth and the preservation of liquid consistence. The adhesive system. It's called Letuche. When the adhesive system evaporates, it goes into a semi-gel state. Filler. Particles of inorganic matter. Silicon dioxide, acrylcyl. Micro and nano size. Increases the strength and stability of the hybrid layer. Prevents the appearance of gaps between the filling and the tooth. Compensates for a load at the tooth filling interface. Initiator, a chemical substance that starts the reaction with the formation of free radicals, which contribute to the interconnection of metacrylates into a single organic matrix. In the photocomposite, it is camphorquinone. In chemical composite, benzoyl peroxide. Stabilizer, a chemical substance that prevents spontaneous interaction of monomers in the components of adhesive system and their premature polymerization. Determines the shelf life of the adhesive system. Activator, provides self-curing adhesive system. In photocomposite, it is light halogen from photopolymer lamp. In a chemical composite, it is tertiary amines. Classification of adhesive systems. By generation, it can be 1, 2, 3, 4, 5, 6, 7 generations. By the amount of filler, unfilled, filled, and nanofilled. By type of solvent containing acetone, alcohol, water-based, combined. By appointment, enamel dentin for all photocomposites, universal for photocomposites, chemical composites, and dual-curing materials. Multifunctional for composites materials, ceramics, amalgam, and alloys. According to the polymerization method, light curing, self-reinforcing, double curing. According to the mechanisms of action, self-etching, 1-step and 2-step. Adhesive system with total etching of tooth tissues, 2-step 2-component and 3-step 3-component. Classification of composite materials according to the particle size of the filler by Lutz and Phillips, 1983. Macrofield. It includes from 8 to 12 micrometers or more, and this hybrid can be macrohybrid and totally completed. Include inorganic filler. Mini-field from 1 to 5 micrometers. It's hybrid, in class hybrid. Microfield from 1.04 to 0.4 micrometers. It can be microhybrid, nanohybrid. Include organic matrix. according to the curing method: thermal, chemical, light, double, chemical and light. By consistency: normal consistency, fluid, packable. By chemical composition: traditional composite materials, Ionomer, organically modified ceramics. By appointment: for the achieving group of teeth, for the frontal group of teeth, and universal. According to the release form: powder and liquid, paste. It is the chemical composite materials in separate jars, syringes. Paste or gel in syringes. Paste or gel in capsules. And we see in picture syringes, and these three, it is a capsule. Chemical curing composite materials. One component, paste, contains a chemical activator self-curing reaction, tertiary aromatic amines. Two component, paste, chemical polymerization initiator, benzoyl peroxide. When mixed, free radicals of the polymerization reaction are formed. Chemical curing composite material properties: positive, uniform polymerization, easy of use, minimum mixing time. Availability. Negative properties of chemical curing composite materials: darkening of the filling, amine staining due to uncreated residual activator. The complexity of the dosage. Low aesthetics. Low wear resistance, porosity when mixing components, and toxicity. Composite materials of chemical curing. Representatives: composite from foam alpha dent, avicrol from spova dent, degufil SK from degusa, compolux from foam septodont, and charisma F from foam culture. Light cured composite materials. Photocomposites. Photo activator, self-curing reaction, light of polymer lamp. One component, paste, photopolymerization initiator, camphorquinol. Hybrid composite materials, Macro. Positive properties. Aesthetics. Sufficient straight. Better quality of the filling surface than macro filled ones. X-ray contrast. Negative properties of hybro-composite materials. Macro. The surface of the filling is worse than that of microfills. Representatives. It is a prismafill and polyfill supra. Hybrid composite materials micro. Positive properties. Aesthetic, physical and mechanical properties. Polishability. Quality of the surface of the seal. Color fastness. And representatives, it is a tetric and T-econom plus. Negative properties of microhybrid composite materials. The surface is worse than that of microfilled ones. Insufficient strength and spatial stability. Height polymerization shrinkage. Representatives charisma and Herculite XRV. In this picture we see a representative of this prodigy, Prisma TPH, Unirest by Stomodent and Walix Plus. Totally made composite materials. Inorganic particles, macro, mini and micro. They have a modified organic matrix, low shrinkage, the property of the chameleon, that is the ability of filling to acquire the optical color of the tooth. Well polished. Representatives, it is a arabesque top, Filtic Z215 and tetric ceram. Nanohybrid composite materials. For the first time, the term nanotechnology was introduced in 1974 by the Japanese researcher Taniguchi. Nanos from the Greek dwarf. Nanotechnology is a technology that operates on the order of a nanometer. 1 nanometer is 1 to 1 million, 1 billionth of a meters or 1,000 of a micron. This is 10 times the diameters of a hydrogen atom, 80,000 less than diameter of a human hair, hundreds of times smaller than a wavelengths of visible light. The first representatives of nanocomposites is Filtec Superm, inorganic filler, silicon zirconium filler of spherical shape from 5 to 75 nanometers. Part of the particles, nanometers, are combined into complexes, nanoclusters. Their size is from 0.6 to 1.4 microns, which allows filling the material up to 78% by weight. This gives the material high straight. And in this picture we see Filtec Supermer XT. Properties: high straight fast gloss, low shrinkage, the effect of chameleon, plasticity, does not stick to the tools, and 34 shades. Representatives: Grandeur, Premium, and Filtec Supermer XT. Fluid composite materials, introduced in 1977. They have a modified polymer matrix based on highly fluid resins. May contain microhybrid or microphilic filler. Some materials emit fluorine, which determines the anti-carious effects. Produced according to the degree of fluidity, medium and high flow. Produced in special shrinkages. Due to the property of thixotropy, the ability to spread, it penetrates well into hard-to-reach areas and does not flow back from the surface. Condensable, packable composites, created as a substitute for amalgam, prepared on the basis of a modified thick matrix and hybrid filler, particles up to 3.5 micrometers. Basis properties: very high straight, close to amalgam, high resistance to abrasion, dense consistency, condensance, does not flow, does not stick to the tool, low polymerization shrinkage. And representatives: it is Solitaire 2 and Filtec P16. Compomers: glass ionomer cement plus composites. It is a combination of acidic groups of glass ionomer polymers and photopolymerizable groups of composite resins. Under the influence of light, the composite component polymerizes. The glass ionomer reacts via water binding, forming a fine structure within the cured composite matrix. Armatures, organically modified ceramics. The organic component is a multifunctional matrix. Inorganic component, glass and ceramics. Properties: straight, biocompatibility, good polishability, low shrinkage. Representatives: defined core, admira, Ceram X. That's all for today, and thank you for your attention. Goodbye.